Hey there folks, Professor G here, and today we're going to talk about rocks and the rock cycle. We're going to start with the definition of a rock. You've had definition of a mineral already, and that had 4 components to it. This one is a little similar, and I worry that you guys might mix the two up. So depending on how your brain works, you might want to start it differently. If you want to start the definition of rock differently, you would say naturally formed, inorganic, or organic, blah, blah, blah. If you don't mind them starting off similarly, well, naturally occurring is a great option. Naturally occurring, inorganic, or organic, blah, blah, blah. Okay? So, just like with minerals, when we say naturally occurring, it means that it occurs naturally in nature. It's not man-made, woman-made, squirrel-made, as I like to say. Okay, it just is. From there, the similarities end because of one big thing here: the fact that rocks can be organic. Remember, with minerals, no, absolutely, positively, all minerals are inorganic. Not organic. Rocks, on the other hand, can be. Coal is a great example. Coal comes from plant material. Anywhere there was a swamp or a marsh, you're quite likely to get a vein of coal, a layer of coal in the rock record. Consolidated aggregate. All right, what does that mean? Well, it means to consolidate means to bring things together. An aggregate is a whole bunch of different things. So we want to bring a whole bunch of different things together. Okay, like what? Well, here's where the last part comes in. Grains of one or more minerals, or even fragments of rocks, right? And this organic material that we mentioned. So, just like I told you with the minerals definition, you could remember this as bullet points in your brain, or you could remember it as a little sentence. I like this sentence myself. Naturally occurring consolidated aggregate of organic material and or inorganic mineral grains and rock fragments. All right. Doesn't have to be word for word, but I'd need to see the natural, the inorganic or organic, and then talking about what the pieces parts are. Okay? All right. Hopefully, at this point in your life, you know that there are 3 types of rocks out there in the world. 3 big categories: igneous rocks, sedimentary rocks, and metamorphic rocks. In geology, we're going to talk about each of these in depth, and even some tangentially related chapters. It's a big branch off right here. In earth science, we really don't go into it that much. We talk more about the tangential stuff, than like earthquakes and volcanoes under the context of geology. Whereas in geology, we're going to talk about igneous rocks themselves and also talk about volcanoes. With sedimentary, for example, I didn't give you this a moment ago, but we'll talk about sedimentary rocks, we'll talk about weathering and erosion, we'll talk about soils, wherein beyond this lecture, for sedimentary rocks, we might only touch on soils in earth science, and so on and so forth. So earth science, you don't get the in-depth because we have so many other topics to talk about. Okay, but geology, well, we've got lots of nice chapters in the books for this. So let's get you a little bit of information about each of these 3 before we get too much further. Igneous rocks are rocks that form from cooled lava or magma. Okay, lava and magma are essentially the same thing, but depending on where they are, the geologists call them slightly different things. They call it lava when it's at the surface of the earth, and they call it magma when it's inside the earth. I told you it has to cool. Once it cools, crystals of minerals start to grow. And basically, different assemblages of different minerals they've just come to recognize as different igneous rocks. You've heard of granite before, okay? Granite is nothing more than a mixture of quartzes, feldspars, some micas. That's what an igneous rock is, okay? So cooling, crystallizing, minerals grow, magma or lava. Sedimentary rocks. Sedimentary rocks, these are kind of the chicken McNuggets of the rock world. Okay, you've got all these different sorts of pieces, parts lying around at the surface, and they get kind of like the definition we just left, right? They get brought together and glued together and presented to you as a new rock. Sedimentary rocks are made of sediment. There is another type of sedimentary rock which we will acknowledge in geology, and those sedimentary rocks actually grow in water, crystal by crystal, kind of like how igneous do, but not out of magma or lava. They grow in water. But most sedimentary rocks that you're familiar with were just, I don't want to say dirt lying around at the surface, but sediment lying around at the surface, sand, gravel, pebbles, that kind of stuff. Glued together. Lastly, metamorphic rocks. As the name implies, metamorphism, metamorphosis, something has changed. What changed? Well, the rock itself, okay, is a metamorphic rock is a pre-existing rock that changed into a new rock. It changed due to exposure to very high temperatures and very high pressures. This is something you typically need to drag it down into the earth to do, but also it can get caught up in some plate tectonic kind of activities, and you could get these very extreme pressures that way as well. So you take an igneous rock or a sedimentary rock and you expose it to these high temperatures or pressures, you get a metamorphic rock. And yes, it's true, you can also metamorphose a metamorphic rock. We'll worry about that later. But so you take an existing rock, you change it because of high temperatures and high pressures, and you get a new rock. So that's really it for now with the explanation of these three. Like I said, in geology, you'll get a chapter for each of these and then some. In earth science, you'll mostly just kind of poke around with it and lab a little more, and we'll leave the definitions at that. Okay? All right, so let's move on then and talk about this rock cycle thingy. The rock cycle basically shows us how all of these three rock types that we just discussed are related, how they're connected, how they form, how one is recycled into another. Okay, Mother Nature was the first recycler. And along the ways, we're going to show you the origins and processes. I'm going to have you draw this in a minute. Don't start now because I'm going to tell you how to do it in a very specific way. What we're going to see is that these rectangles here, these are going to be objects, if you would, okay, nouns. The arrows connecting the blocks, those are the processes. And I think that'll help with the understanding of this one if we realize that arrows are one thing and blocks are something else. So what I want you to do here in a moment, when I'm done explaining to you, is just pause this for a moment and draw these 1, 2, 3, 4, 5 rectangles. You don't need to make them three-dimensional or anything like that. And don't even label them yet, okay? Don't even label them, but draw these 5 blocks. And I'm going to use a clock analogy, if you would, on your piece of paper. Use about half a sheet of paper. Draw one at 11 o'clock, 1 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock. Do not worry about down here, and do not draw any arrows yet. All right? Okay, hit pause. Alrighty, so you are back, and you have 5 blank rectangles on your sheet of paper. Let's start annotating. All right, it's a circle, it's a cycle, right? There is no beginning, there is no end. but there's usually a logical place to start. In this case, that logical place to start is over here at 9 o'clock, where you see the word magma. Now, you could write the word magma, but I also want you to write in the word lava. Magma or lava, you can say. And I want you to do that to remind yourself of a couple things. One, that they could both make igneous rocks, or igneous rocks can come from either of them. We also want to remind you that they're essentially the same thing. Okay? All right, so you have magma. Sorry, my mouse is disappearing here. Magma or lava. And up here, you could even write the word igneous rock right now. Do not, however, write this word solidification. That is useless. Means made solid. Make solid. So magma is made solid, and it's now igneous rock. Well, yeah, we could have figured that out. A 3-year-old could figure that out. Rocks are solid. Let's put something a little more useful in, right? What was the process that we discussed a moment or two back? The magma or lava cools, and what happens? Crystals grow, right. Let's put the word crystallization in there. Crystallization. You could even write cooling and crystallization if you want. More detail you put in, the better, I suppose. So magma or lava cools and crystallizes, forming igneous rock. Wow, actually you can read it like a sentence now. All right, from igneous rock, we want to go over here, and you could write the word sediment. All right. Sediment, remember, are those pieces parts. And you could even draw this arrow and write the words weathering and erosion. But somewhere, probably down underneath your drawing here, I want to take a moment to talk about these two vocabulary words. All right? Especially for earth science, because we might not touch on them again. But in geology, it's a great introduction to them. They'll have their own chapter soon. So weathering and erosion, you might think are almost synonymous. They go hand in hand, after all, but they are quite different words. Weathering means to break down. Okay, weathering is the breakdown of materials at the surface of the earth. Weathering produces sediment. Erosion, on the other hand, erosion is movement, transportation. And the problem really comes in with the way that folks in the world use the word erosion. They usually will say wear away, something similar. And the problem with that is that's actually two processes. The wearing is the weathering. The away is actually the erosion. Okay? So, to go back to our definition where we said weathering produces sediments, erosion transports sediments. All right, when we get to that chapter, as I said, you'll see that it's a little more nuanced than just that. But for right now, we'll keep it simple. So, igneous rock gets broken down and transported as sediment. From sediment, we see the sedimentary rock. Feel free to write that down. But we have another sort of generic, kind of useless word here, lithification. Lith means rock. You may have heard of like a monolith, right? Giant hunk of rock. So sediment gets rockified, and then it's a rock. Yeah, okay. So what can we do that's a little more helpful? Well, let's go back and talk about one type of particular. If you think about when we discussed making sedimentary rocks a couple minutes ago, I told you that the material had to be squeezed together and glued together, right? Compaction and cementation are the real proper words there. So instead of writing lithification here, let's write compaction and cementation. Compact and cement. Squeeze them and glue them, okay? And that's how we get sedimentary rock. Now, as I said, there is that other type that grows in water, but let's keep it simple for right now. All right, sedimentary rock to metamorphic rock, You could write metamorphic rock in your little square there. And, you know, fine, you could have the word metamorphism here, but who, you know, let's be a little more specific. I was going to say, who wants to tell us? You guys can't really raise your hand and I could call on you right now, but hopefully you're thinking to yourself, what was that process of metamorphism we mentioned just a few moments back? It was exposure to high temperatures and high pressures, okay? So somewhere in here, along with the word metamorphism, please write exposure to high temperatures and high pressures. So sedimentary rock is exposed. It has to be brought into the earth, usually, okay? It could get caught up in a plate tectonic event, one continent crushing into another continent, and super high pressures involved there could certainly cause this, but typically, we'll, again, keeping it simple right now, gets brought down into the earth where it's exposed to the earth's internal heat, and it changes into this metamorphic rock. All right. Lastly, metamorphic rock over to magma or lava. Well, how are we going to turn a rock back into magma? And that, by the way, is why they use the word magma here. Remember, magma refers to the stuff on the inside of the earth, and we told you we had to bring it into the earth to cause this metamorphism. So if you leave it in too long or you bring it down too deep, it will remelt. All right, so instead of partial melting here, let's use the word remelt. So metamorphic rock remelts into magma. Magma cools and crystallizes into igneous rock. Igneous rock gets broken down and transported as sediment. That sediment gets compacted and glued together and turned into a sedimentary rock, which gets sucked down into the earth, exposed to high temperatures and pressures. Boom. And we have this nice, what we call the outer loop of the rock cycle. Okay? Very nice. Now, we've got this mess in the middle. What's going on here? These arrows are there to remind us that, for example, metamorphic rocks don't come from only sedimentary rocks. Metamorphic rocks can also come from igneous rocks. I suppose you could even have a little arrow pointing back to itself to remind you that metamorphic rocks can come from metamorphic rocks. But here's what I propose, and again, this is why I didn't want you to draw these arrows right off the bat. I think it would make more sense if I was drawing this diagram from scratch, like you are right now. Wouldn't it make more sense to draw this arrow going to the process rather than the product? Because igneous rock doesn't go straight to a metamorphic rock, just like sedimentary rock didn't go straight to a metamorphic rock. It went through the process of metamorphism. So I think more correctly, this arrow should go to the process. Similarly, the arrow going from metamorphic rock to sediment, okay, that should go to the process of weathering and erosion. That metamorphic rock needs to get exposed at the surface of the earth, needs to get broken down, turned into sediment. All right. What else? Oh, yeah, sedimentary rock back to sediment. Well, in order to turn sedimentary rock into sediment, of course, you need to weather it and erode it. This arrow should go up here. Really, the last thing I want to mention here is what seems like this tiny little loop here is actually one of the biggest surface processes going on the planet. Anytime material is exposed to the surface of the earth, it's breaking down. Okay, it's not horribly exciting to be a rock. It kind of just sits there. It breaks down. It might get to roll down a hill or float down a stream. Then it just gets set down, and eventually it dries out, glues back together, and hey, it's a rock again out in the sun. And at which point it starts breaking down again, and you see this loop just goes on and on and on forever. I don't want to say that it's, rare to make metamorphic rocks, but it's really hard to do to, get sucked down that deep into the earth and so on and so forth. Igneous rock gets made all the time, okay, on the ocean floors. It's being made every day at the surface of the earth in volcanic events, all right? So those are also pretty dang common. All right, so that is the rock cycle. Alrighty, folks, and we're back. I want to go beyond the rock cycle for a couple minutes and talk about how rocks are addressed in geology. In this class, we won't get to the point where we're looking at something called geologic maps, but they are, as the name implies, maps of an area that show what types of rocks are on there. We will, however, in this class at some point be drawing some diagrams or looking at some diagrams that for groundwater, for example. And we will need to be talking about what type of rock is the water is in and above it and below it and so on and so forth. And as such, we will be dealing with some of these rock symbols that they use in the real world for making these geologic maps, for drawing some schematics, if you were an environmental engineer, for example, and so on and so forth. You see there's a wide variety, and there's many more. This is just a smattering. Well, in here, we've got my crude renderings of those. We really only worry about 4 types of rocks in here. We've got the bricks, we've got the little dots, we've got the dashes, and we've got stars or asterisks. So we go back here and let's see. Let's see what we've got. Anything that looks like that. There's some little dots. It says that's sandstone. There's some little dashes. It says that's shale. That kind of looks like my little stars. There's bricks. We have limestone. We don't have slanty bricks, though. My little asterisks are supposed to be for igneous. Okay, so they match up pretty well with the international symbols. So we have the bricks. So this one right here, this is limestone. This is sandstone. This is shale. And this is just igneous. You may or may not have noticed that I mentioned 3 specific types of sedimentary rock here, but I just said a generic igneous rock here. And that is one big difference where we do vary from these international symbols here. All right, we don't need to get that specific, and as I said, as we're basically just limiting this to some basic subsurface studies with groundwater, we're really concerned with sedimentary rocks much more than igneous rocks. We really just acknowledge and say, oh, this igneous rock is in the way. But there would be different symbols. Just be happy you don't have to memorize more symbols, okay? So bricks are limestone, dots are sandstone, and dashes are shale. So I thought it'd be kind of cool if we could actually see why those are what they are. This is a photograph of some limestone here. And you see that the way limestone weathers in nature, all right, it does break into these blocks. Now, you can see some layering, yes. Okay, in fact, all sedimentary rock is layered. But more prominently, at least to the geologist's eye, are the fact that it breaks into these brick-shaped structures. So we're seeing the vertical cracks in addition to the horizontal layering. So that's why they draw limestone as bricks. Shale. You've all seen shale. You've probably seen limestone now. You'll recognize it. But everyone's seen and recognizes shale. So you see these lines here. Much more prevalent horizontal fracturing or horizontal layering. Quite obvious here. And sandstone, hopefully that you didn't have to think too much about why we have dots for sandstone. Here is an example of in the real world. This is a section that we talk about quite a bit. This is in, I think this one is right from Utica. This might be my picture. This is what we see as you're going by the Little Falls exit. Okay, it's also a portion of it on your lab book if you're in geology class. And what we see are alternating sections of limestone, the tannish here, and shales. Okay, the darker. And then there's some limestones interbedded up in here, bunch of limestone. And when we get into sedimentary rocks and start talking about environments, and this is something you guys in earth science do miss out on, it's kind of really neat stuff. We actually get to apply, instead of just memorizing rock names, we find out, where they came from and why they're there. What we see is that this is a very common marine sequence that shows us basically the movement of shoreline over time. This right here is offshore, okay, but what we see is that shale is usually formed in shallower water than limestone does. So we see the progression of this spot through time. Okay, and you could draw a line anywhere vertically through here, but we'll just say right here, this spot through time, how the water got shallow and then got deeper and then got shallow again and then deep, shallow, deep, shallow, deep, shallow, deep, shallow. And this is particularly relevant, I guess, in a time when there are still people out there who are saying that sea level doesn't change. Well, here's data right here. Here's actual rock solid evidence, pardon the pun, that it does indeed. Okay, because shale and limestone form in different depths of the ocean. So the only way to do that, well, I guess you could move the continent back and forth, but the much easier way to do that would just be to raise and lower sea level. Okay, imagine if you were standing on the beach, if you're still not really processing what I'm saying. Imagine if you were standing on the beach for 10,000 years, okay? For the first 1,000 years, maybe you're up to your ankles in water. Then 1,000 years later, you're up to your knees. You haven't moved, but just the water level has changed. 1,000 years after that, maybe it's up to your waist. And then it goes back down. Those represent different depositional environments. Different sediments would be deposited, leaving you different rocks. So, and of course, we're dealing on a much larger scale than just a couple thousand years here. So, all right. So that is really just, as I said, an introduction to rocks. In geology, each rock gets a chapter, if not a little more. In earth science, you're going to do most of your rock talking in lab, okay? And we'll move on to some more specialized topics in geology. Take care, folks. Bye-bye.